The purpose of this video is to explain some examples of vector spaces as well as some examples of non-vector spaces. Considering what makes something fail to be a vector space is just as important as understanding why something is a vector space. The first example that we're going to look at is the space of continuous functions. So let's let C, parentheses, minus infinity to plus infinity, be the set of all continuous functions that are defined on the entire real line. In this vector space, a vector is now a continuous function. And so what I've pictured here are two vectors in this space, vector u and vector v. In the last video lecture, I gave the definition of a vector space. Let me go back to the panel. In an abstract vector space, you have a set of objects, and they need not be vectors in Rn. They could be something else, like continuous functions. And what needs to happen is that you can add them together and still get a vector, or you can scalar multiply a vector and still produce a vector. And there are an additional set of 8 rules that need to be satisfied. 8 axioms. So when we think about this new example involving continuous functions, let's check our understanding by checking some of these axioms. Why don't we check axiom 1? Let's make sure we can add 2 continuous functions together and get a continuous function. And let's look at 6. The first 2 things we want to see are that these axioms hold, that the set is closed under addition and scalar multiplication. So here is my little cartoon of my vector space of continuous functions with 2 particular vectors drawn in it. And let's check these 2 very important axioms. Axiom 1, we need to add continuous functions together. Well, these are standard facts from calculus. If you have a function f, which is continuous, and a function g, which is continuous, the new function f plus g of x is also a continuous function. There are standard ways to check this, and this is usually going to involve the limit definition of continuity. And I won't get into those details because that's more of a calculus type exercise, and all of you in this class have had calculus before. It's also easy to check that the set is closed under scalar multiplication. When you take the function cf of x, that's also going to be continuous, which is another exercise in checking the limit definition of continuity. So this gets us 2 of the rules that are on the list. But in order to actually prove that you have a bona fide vector space, you would need to check all 10 axioms and prove that they're all satisfied in order to know that the set of continuous functions over the real line really does form a vector space. So I've made some space here on the page so that we can discuss a couple more of these axioms. All right, so to complete this proof, we would need to check all of them. Maybe we won't do all of them, but we'll do, say, rules 4 and 5 and 6. So the axiom number 4 was that there was a 0 vector in this space. And the 0 vector was such that when you added it to any other vector, you didn't change the vector that you were adding it to. Well, the natural 0 vector in the space of continuous functions is going to be the 0 function. Say g of x equals 0. Of course, if you add 0 to anything, you don't change it, and you still have the same continuous function. This is a very easy axiom to check, and often these axioms are quite easy to check. Axiom number 5 stated that every vector needed to have an additive inverse. And the natural thing to do when you're dealing with continuous functions is just to change the sign of the function. F plus minus f is certainly going to give you the 0 function. And when you visualize this, your function looks like the reflection across the x-axis, which is what's depicted here. F plus minus f will give you the 0 function. And clearly, if you take the real number 1 and multiply times any function, you get that function back. So axiom 10 is also an easy one to check. The rest of the items on the list, which I will scroll back to briefly, involve a little bit more work. Perhaps you may have to do a bit of calculus and work with the definition of continuity to check that what you produce is still a continuous function. But if you worked through all 10 of these, then you would have a proof that the space of continuous functions is indeed a vector space over R. I want to now discuss several examples that involve polynomials. In the Introduction to Vector Spaces video, we discussed the example of polynomials of degree at most 2 and saw that they formed a vector space. Well, what if we take, as our second example today, polynomials of degree exactly 3? Well, these do not form a vector space. So what is it that's going wrong? Well, I have here an example of 2 polynomials. Let's take p and q to be something like 7 minus x cubed and 1 plus x cubed. These are both polynomials of degree exactly 3. Well, clearly when you add these together, the x cubed parts are going to cancel. P of x plus q of x is still a polynomial. That's true. But this is going to be the polynomial 8 plus x. The problem here is that p plus q is a polynomial of degree 1. So it falls outside of the set V. If your set V consists of only things of degree exactly 3, then this is not closed under vector addition. So axiom 1 becomes an issue. U plus V is not a polynomial of degree 3 in general. And also axiom 4 is going to be an issue. You need to have a zero vector in your vector space, but the zero vector is a constant polynomial equal to 0 in this case. And it is not degree 3, it's degree 0. So for a variety of reasons, we see that polynomials of degree exactly 3 do not form a vector space. And for the same reasons, polynomials of degree exactly 2 or degree exactly 5 or degree exactly 1 also do not form a vector space. However, if we take polynomials of degree less than or equal to n, it is a vector space. This is much like the example of polynomials of degree at most 2, which we discussed before. But here, the operations of vector addition and scalar multiplication are closed. They are well defined. And these sets of polynomials do form a vector space. Another example that's really closely related to polynomial examples are spaces of matrices. So, for our fourth example, the space of all m by n matrices does form a vector space. There are lots of axioms to check to convince yourself this is true. Axioms 1 through 3 are going to come from the way that matrix addition works. So if you add two matrices together, A plus B is also going to be m by n. So it's clearly closed under vector addition. Matrix addition is commutative and obeys all the rules that we expect. The zero vector in this vector space is going to be the m by n matrix that's populated by all zeros. And the additive inverse of a matrix is just going to be minus a, meaning I'm taking scalar multiplication by minus 1. And all of the usual properties of scalar multiplication that we've been working with matrices give us the rest of the axioms 6 through 10. So there's a remark to be made here, and that's that thinking of vectors, thinking of matrices, and thinking of polynomials is not really all that different in terms of examples of vector spaces. It's really just a different way of packaging the same information. For example, we can think of a vector as a matrix. It's an n by 1 or a 1 by n matrix, depending on whether you're writing it as a row or a column. Or we can think of a matrix as a vector. By the way, in the context of this remark, I mean a vector in Rn. So for example, if I have the matrix 1, 2, 3, 4, this is a 2 by 2 matrix. I can kind of associate this with a 1 by 4 vector, 1, 2, 3, 4, by writing out all of the entries in a list. I could also think about this as determining a polynomial. I could think of these as the coefficients of a degree 3 polynomial, 1 plus 2x plus 3x squared plus 4x cubed. And I can go backwards with these arrows as well. So this is something for you to ponder, but these examples of vector spaces made out of m by n matrices, polynomials with real coefficients, and then your traditional vectors in Rn are not really all that different. So let's pivot our discussion a bit now and think about examples and think about constructs that get us away from these standard examples that are essentially all equivalent to each other. One good exercise in doing this is to try and prove some properties of scalar multiplication without relying on their properties as vectors in R2, R3, or Rn, just using the axioms that define a vector space. So there's a theorem. You can find this in your textbook. And it is called the properties of scalar multiplication. So if you have a vector v, and you have any scalar, then what has to be true are 4 properties. First, if you multiply your vector v times 0, you'll get 0. Second, if you take a scalar multiple of v and you get the 0 vector, then that must have meant that either the scalar was 0 or the vector that you started with was 0. If you have a scalar c and you multiply times the 0 vector, you get the 0 vector. and that if you multiply your vector times -1, you get minus that vector. These are all extremely sensible. You might not be inclined to think twice about them, but they're all statements that require a proof that uses the axioms. So let's take one of them and work through a proof of it that does not rely on anything to do with n-dimensional Euclidean space. Let's take property number 3, for example. If you scalar multiply the 0 vector, you get the 0 vector. Now, why would this be true? So let's walk through an axiomatic proof of this, property 3. So we're going to start with axiom number 4. What we want to show is that scalar times 0 vector gives you 0 vector. Now what axiom 4 tells us is that if we take any vector u and we add it to the 0 vector, we get u back. So this also applies when u itself is equal to 0. This tells us that 0 plus 0 is equal to 0. And that's what's stated right here. So this is just a statement of axiom 4 in the case that u is equal to 0. Next, what we're going to do is apply axiom 7. So if we take 0 and then write it as 0 plus 0 in parentheses, axiom 7 tells us that we can distribute the scalar across the parentheses like this. And then next what we're going to do is a little bit of a trick. So we're going to take CO equals C0 plus 0 and add minus C times the 0 vector to both sides of the equation. And that's what we see written here. Next up is another axiom. We're going to apply the associative axiom to the right-hand side in order to rearrange the parentheses. And that leaves us with C times the 0 vector plus minus C times the 0 vector is equal to this expression. Then we're going to apply axiom 5. Axiom 5 tells us that every vector has an additive inverse, and when you add them together, you get the 0 vector, which means that this can be written as the 0 vector. And then what's left is to apply axiom 4 one more time to rewrite C0 plus 0 as C0. And then what we're left with is 0 is equal to C0, which was what we intended to show. So you have to be a little bit painstaking and careful, but all of these properties can be checked by applying the axioms. Let's now take a look at some examples of things that are not actually vector spaces. The first example we're going to consider, example number 1, is the set of integers, not the set of real numbers. And this is not a real vector space. Can you think of why? If you take two integers and you add them together, you still get an integer. The distributive law should work the same way. The associative law should work the same way. Addition is commutative when you're dealing with integers. The problem is scalar multiplication. Take, for example, any real number that is not an integer. For example, 1/2 or 1/3 or 1/7. And scalar multiply that times the vector. And by vector, I mean here an integer. Well, this is going to give you something which is not an integer. And so it is no longer a vector. This is not really a vector space, but it would be no longer considered an integer, which is what we're trying to make into a vector. So it's not a vector space because it is not closed under scalar multiplication. Let's take a look now at another example. For our set, what we're going to take is R2. So regular old Euclidean two-dimensional space. And we're going to add vectors together the way we usually do, but we're going to redefine the rule for scalar multiplication. Our redefined scalar multiplication is going to tell us that if we take a scalar c and we multiply it times a vector, it's going to multiply into the first entry, cx1, but the second entry will become 0. This is going to turn out to not be a vector space, but let's try and pinpoint the exact problem. For a quick little example, if we had the vector 1, 4, and we multiplied by the scalar 2, that would give us 2, 0. If we have the vector 9, 2, and we multiply times -1, that's going to give us -9, 0 in this newly defined space with a slightly different version of scalar multiplication than is the usual. So the strange thing about this example is the first 9 axioms actually all hold. Let's check a couple of them. Remember, if you're trying to show that something is a vector space, you have to go through the entire list of 10 axioms, and if all of them hold, you have a vector space. If you're trying to show something is not a vector space, all you need to do is find one axiom that fails to hold in one case, and that provides the counterexample for you to say that it's not a vector space. But if you were running down the list in order for this example, it would take a long time because the first 9 would check out. Let's think about axiom number 1. Axiom number 1 tells us that if we add 2 vectors together, we get a new vector in this space. So if we add 2 vectors in R2 together, we still get another vector in R2. That's just going to hold. And things actually do have additive inverses here as well. The additive inverse of x1, x2 is just minus x1, x2. Let's spot check axiom 7. It'll take a little bit more effort. So what axiom 7 states is that if you take 2 vectors u plus v and you scalar multiply by c, it's equal to cu plus cv. So this is what we want to work out. Actually, what I've written down here in the notes is a bit more consolidated, so let's work this out carefully to check this axiom. All right, so let's take cu plus v and see what that is. Okay. So our u, by the way, is something that we would write as x1, x2. And our v is what we're going to call x1 prime, x2 prime, to be consistent with the previous 2 axioms that we checked. So a scalar times a u plus v means we're taking a scalar times x1, x2, plus x1 prime, x2 prime. And we should follow the order of operations carefully and work from the inside out with these parentheses. So that means we're going to be adding component-wise, because that's how vector addition works in the vector space that we're, or rather non-vector space that we're considering. And so we add together the x1s, and we add together the x2s. And now it comes time to do scalar multiplication. But our rule for scalar multiplication is wonky. It's going to turn that second coordinate into a 0. So as we follow that rule, we see that this is going to be, in the first entry, c times x1 plus x1 prime, and in the second entry, just 0. Okay, now we can continue manipulating this expression. Let's distribute the c into this parentheses, just using how real numbers work, following the rule for bona fide real numbers. So that'll give us, in parentheses, which is our vector notation, cx1 plus cx2, comma 0. And then we can split this into 2, that should be an x1 prime. We can now split this up as the sum of 2 vectors. This is equal to cx1, 0, added to cx1 prime, 0. And these 2 sum ends are equal to the scalar times x1, x2, plus the scalar times x1 prime, x2 prime. So at the very beginning of this chain of equalities, we have cu plus c times u plus v. And at the end, what we have is cu plus cv. So we've shown that they're equal by carefully following the rules. I think it's a good exercise to check the other remaining axioms that we didn't check. And then, having checked all but the last one, we get to axiom number 10, and something's going to go wrong. So what happens with axiom 10? We're supposed to be able to multiply the vector times 1, and then it's not supposed to change. This is where the problem is, because 1 times x1, x2, the way we've defined it, is going to be x1, 0, and this is not equal to x1, x2, our vector u. So this is where everything breaks down, and we have to conclude that this space that we defined is not going to be a vector space.